Hi everyone, I'm John Turilla, one of the authors of Topology, a categorical approach. In this video, I'm going to talk about paths in a topological space. Before I start, let me say that you may have noticed that the unit interval, that is the set of real numbers greater than or equal to 0 and less than or equal to 1, plays a very prominent role in topology. The unit interval is used to define paths in a topological space, which are continuous maps from the interval into the space. And from the concept of paths, one can define the functors pi0 and pi1, which I'll review later in this video. And the interval is also used to define homotopies between maps. Recall that if f and g are maps from a space x to a space y, a homotopy from the map f to the map g is defined to be a map from x cross the interval to y, which when viewed as a one-parameter family of maps from x to y, parametrized by points in the interval, it starts at f and ends at g. Why does the interval play such a fundamental role in topology? Is it just an accident of development or anthropological, a cultural choice like using base 10 to write numbers? The interval, as it turns out, has a couple of very special properties. Namely, it has two distinguished points, 0 and 1, and when you glue the interval to itself by taking two copies and gluing the 0 of one interval to the 1 of the other interval, the result is homeomorphic to the interval itself. In this picture here, you see that when you glue the unit interval to itself, you obtain an interval of length 2, which is homeomorphic to the unit interval. The map t goes to 2t, defines a homeomorphism. In a way that can be made very precise by a theorem of Peter Freyd, the unit interval is universal with respect to this property. It's the universal space that has two special points that when you glue along the special points, you obtain something homeomorphic to the original. And the fact that the interval can be doubled and glued together to get itself implies that the set of maps from the interval into a fixed space x has an algebraic structure. A path, which is a function from the interval, has a starting point and an ending point. Then, if the end point of one path is the same as the starting point of another, the paths can be concatenated to form a new path. So, if f is a path from A to B, and g is a path from B to C, we define a new path, gf, from A to C by splitting the interval in half and doing f on the first half and g on the second half. When you encounter a new algebraic operation, it's natural to wonder about its properties. One of the first things you'll notice is that path concatenation isn't associative. Compare H concatenated with GF to HG concatenated with F. The concatenation of H with GF is the path defined by doing GF on the interval 0 to 1/2 and then doing H on the interval 1/2 to 1, which means you do F for 1/4 time, G for 1/4 time, and then H for half the time. On the other hand, HG concatenated with F is the path that does F for half the time, followed by HG for half the time, resulting in doing F for half the time, G for 1/4 of the time, and H for 1/4 of the time. So the image of the paths H concatenated with GF and HG concatenated with F are the same, but as functions from the unit interval into the space, they are distinct functions. I'll return to this later. Now, we can define a relation on a topological space X by saying that a point X is related to a point X prime if there's a path from X to X prime. This relation is reflexive, since for any point X in a space, the constant map from the interval to X is continuous, and so defines a path from the point X to itself. The relation is also symmetric. If f is a path from x to x prime, there's a path going in the other direction. Call it F inverse, defined by F inverse of t is F evaluated at 1 minus t. That's a path that starts at x prime and ends at x. And path concatenation shows that the relation is transitive. Given a path from x to x prime and one from x prime to x double prime, the concatenation of these paths defines a path from x to x double prime. The equivalence classes of this relation are called the path components of x. And if every 2 points of x can be connected by a path, using the terminology I just defined, that's saying that x consists of a single path component, then we call the space X path connected. Path connectedness is preserved by continuous surjections. You can see this if you have a surjection from a path connected space X to a space Y, and you're given 2 points of Y, you can choose a preimage in X for each point. Then there's a path between those points of X because X is path connected, which by composition with the surjection defines a path between the points of Y. Therefore, being path connected, being preserved by continuous surjections, implies it's preserved by homeomorphisms, so it defines a topological property. Path connectedness is preserved by taking quotients because quotient maps are surjective. Also, any map from x to y induces a function from the path components of x to the path components of y. If A is a path component of x and f maps x to y, the image f of A is path connected, hence containing exactly one path component of y. Sending A to this path component defines a function from the path components of x to the path components of y. Now, assigning to a space x the set of path components is compatible with composition of functions and identity functions, and therefore assembles to define a functor called pi 0. Now, path connectedness is a nice topological property, and knowing the definition, you can prove things about it. For example, the product of spaces is path connected if and only if every factor is path connected. You can prove that path connected implies connected, but not conversely. And looking for when connected will imply path connected will lead you to properties like locally path connected. But instead of proving any of those results, I'm going to return to the idea of path concatenation and the fact that it does not define an associative operation. The way in which path concatenation fails to be associative is relatively mild. And in fact, concatenation defines an operation that is homotopy associative. So let me tell you what a homotopy between paths is. If f and g are paths from A to B, then a homotopy from f to g is a homotopy between the functions f and g that fixes the endpoints. That is, it's a map H from the interval across the interval so that T0 maps to FT, T1 maps to GT. That's what it means to be a homotopy from F to G. And in addition, for all homotopy parameters S, 0S maps to A and 1S maps to the endpoint B. You might wonder why homotopies between paths are required to fix the endpoints of the paths. You might remember that one of the important properties of the interval is that it has two special points, 0 and 1. And so the endpoints of the path are special too. What happens if we don't require homotopies to fix the endpoints? Well, then every two paths in the same path component would be homotopic, like these two paths pictured here. You can wind one of the curves back to its starting point, move the starting point along any path to the starting point of the second curve, and then grow it until it becomes the second curve. And think of this movie as describing a homotopy. Each moment in time, S, in the unit interval, being one frame in the movie. Now, back to path concatenation. The mild reparametrization required to go from H concatenated with GF to HG concatenated with F shows that these two ways of concatenating three paths result in homotopic paths. Also, the constant path at each endpoint works like an identity from concatenation up to homotopy. And finally, for a path F from A to B, the inverse path, F inverse from B to A, serves as an inverse up to homotopy, meaning that F inverse concatenated with F is homotopic to the constant path at A, and F concatenated with F inverse is homotopic to the constant path at B. This begins to describe a very interesting algebraic structure on the set of paths in a topological space. To make it simpler, you can pass to the homotopy classes of paths. Then concatenation, when it's defined, meaning when the endpoint of one path is equal to the starting point of another path, concatenation will define an associative operation which has identities and inverses. That is, it defines a groupoid called the fundamental groupoid and is denoted by pi1. To summarize, pi1 of x is a category whose objects are the points of x. Morphisms between the points x and y are homotopy classes of paths from x to y. Path concatenation defines composition, and the homotopy classes of the constant maps define the identities. And this doesn't just define a category. It defines a category in which every morphism is an isomorphism, because every homotopy class of paths is invertible. And a category in which every morphism is an isomorphism is called a groupoid. That's the end of this video. Thank you very much for your attention.